The second lecture on electrostatic field, electrostatic energy. In the earlier class, in the earlier lecture, we found out that for the discrete distribution of charges, the electrostatic energy of a system of discrete charges is governed by this is the energy, and which can also be written as this is for discrete distribution, discrete point charges, or discrete point charges. And for continuous distribution of charges, the expression was found to be this is for continuous distribution of charges. That is and then we applied this theory to the system of conductors, and especially to a capacitor. Today we shall first express this electrostatic energy in terms of the field vector. So our objective is to express the field energy in terms of field vectors. We start with this expression and replace the rho by Gauss's theorem and of electrostatics. So this is divergence of D at R times phi of R dV. Here we have used the Gauss differential form of Gauss's law in dielectric medium, where rho is the free charge density. This has two terms. One is phi times divergence D, which is this, and another term is whole thing is integrated over V, the volume, where V is the volume in which the charges are defined. At this point, we like to say that this is the volume V, where the charges are enclosed, and in this case, within this, rho is not equal to 0. We may assume the volume to be this, where rho is 0 for region outside V. So we have come to, from this volume, we have come to a volume, larger volume tau. The closed surface is S, and the closed surface bounding tau is sigma, where we may assume tau to be a sphere of radius r. In that case, sigma is the surface element, closed surface bounding sigma. In that case, we can call it that we can go to a larger volume V, and we apply this and for this we write simply E of R. If we convert this thing to a surface integral, then this comes out to be 1 upon closed surface integration over sigma this is the surface integration, and this remains the volume part. Now you consider this. If we integrate it on the surface of a sphere of radius r, if we assume that this is a sphere of radius r, then on the surface of the sphere, this varies as 1 by r, this d varies as 1 by r square, and the surface area varies as r square. So overall variation is 1 by r, and which goes to 0 as r tends to infinity. That is to say, this integral goes to 0 in asymptotic region. On an asymptotic sphere. So we are left with this expression. This is the expression for the energy of an electrostatic system in terms of the field vectors. We immediately can speak of energy density. This energy density, you can immediately speak of energy density, and we write it as U of r dV over all space, where U of r is equal to E at r times d at that same point. This is the energy density. Energy density, that is energy per unit volume. And if for a linear isotropic medium, this is epsilon 0 E square r, or it is d square r by epsilon. This is the energy density. This expression, this is the general expression, and these two are valid only for linear isotropic and homogeneous dielectric, where this is not necessarily epsilon 0, it may be epsilon. So we expressed this energy density in terms of field vectors, and the result is there. If we write it in terms of it is epsilon by 2 dV over all space. One astonishing thing is that this second or first or second expression could be, the U could be positive as well as negative, as is evident from here. If V, rho and phi are of opposite sign, then U will be negative, and so the total energy could be positive as well as negative, but this is essentially 0, greater than 0. This is essentially positive because epsilon is a positive quantity and it is the square of a vector. So what is the difference between these two? One generally speaks of that this term includes self energy, but this includes only the interaction energy. So this is this is only interaction energy. This is said to have interaction plus self energy. I will prove it for a special case. Let us consider two charges, Q1 and Q2. They are placed at points R1 and R2, and we are to find out the field at R. So I have a charge Q1 at R1, another charge Q2 at R2, and we are to find out the field at R. So this distance is capital R1, which is equal to R minus R1, and this distance is capital R2. This is R minus R2. So the field of one at R, this is K0 1 upon 4 pi epsilon 0 Q1 R1 vector by R1 cube, and similarly E2 at R is K0 Q2 R2 by R2 cube. So the resultant field E is given by which is the quantity just given by this. So the energy density or energy, sorry, electrostatic energy is epsilon 0 by 2 E square R dV over all space. I am for all space so for this I write this is the energy expression. These two are independent terms because this energy expression, this is the expression of energy only when there is the charge Q1, no charge Q2, and this is the energy for the charge 2 only. So these energy terms survives or even if the only one of the two charges are there. That is to say they expresses their self energy, and this is the term which represents the interaction energy. So this is what we call self energy, and this is interaction energy. We earlier found that the interaction energy between two pair of charges is given by K0 Qi Qj by Rij. Let me show that this term indeed represents such an energy. So we consider W is equal to this expression epsilon 0 by 2, these two cancels out. So this is epsilon 0 integral E1. I am just omitting the arguments R. Now you know the expression for this. This is epsilon 0, and there will be kg k 2 k naught, so k naught square q1 q2 and within integral I will have r1 by r1 cube dot r2 by r2 cube dv integrated over all space. We rewrite this term in terms of delta. This minus sign will be dot. Where gradient of 1 by R2 is minus R2 by R2 cube, that's why the negative sign. We express this part as like this. We consider this as two functions. One is this one, another one is, let me write it, 1 by R2. So gradient, if we take the gradient, it is this dot gradient of this, which is the first term. So we need to subtract the extra term included. Extra term included is minus 1 upon R2 gradient of R1 dot R1 cube dv. So what we did, we first started with this expression and used the expression for E1 and E2 as given by this on, and now this part has been written, replace that grad of 1 by R2 is equal to minus R2 by R2 cube. That's why a negative sign has been brought, and this is the term. We have now written it as a divergence of this thing. So this is divergence, this is this dot gradient of this, which is this term. So a minus term has to be added. Now this quantity can be converted into a surface integral, and the surface integral, if we go to a surface at very large distance, then we can, their contribution will go to 0. So this is minus epsilon 0 k naught square q1 q2 and this term will be plus epsilon naught this volume integration will be this is 0, because we have performed this integration over a surface surface of a sphere of radius capital R, which is very high. In that case, this will go as 1 by R, this will be 1 by R to the power 4, and there will be a variation of R square. So overall variation is of the form 1 by R, which goes to 0. So the result is this. This term is simply 4 pi delta. 4 pi delta of R1. R1 means R minus R1 vector. So the 4 pi factor comes out. So 4 pi epsilon 0 is 1 by k0. So there will be a cancellation, and the term that remains is delta of R minus R1, and in the denominator I have R minus R2 integrated over V. It includes all space, So the result is epsilon 0 4 pi cancels 1 k0. So what is k0 q1 q2 k0 q1 q2, and this upon integration becomes 1 by r1 minus r2, which is nothing but this one. So we can again conclude that this is the term only included when we express u in terms of, so whenever we write u as rho phi dv, this includes only this interaction term, and whenever we write u as epsilon by 2 e square dv, these two terms are also included. That's these two terms are indeed very high. That's why this part is always positive. This expression of energy is always positive, while this interaction term or this term could be positive as well as negative. Now let me come to the self energy. This is called the self energy of a point charge. So we consider a charge, a point charge, and what is its self energy? Self energy, if we want to calculate self energy, we consider this is the charge q, and if we consider a distance away from r distance away, then the field at the self energy of a point charge. So the field over here will be k0 q by r square. This is the magnitude, and the energy and dv, due to spherical symmetry, we write dv upon performing the angular integration is r square dr. So the energy du would be E of r, 4 pi r square dr, and there will be another term epsilon 0 by 2. So it will be 4 pi epsilon 0 by 2 this times e square, this is e square is k0 square q square r to the power 4 r square dr. So 1 k square cancels with this, so this is k0 by 2 q square and dr by r square. So the energy is obtained by integrating it from all space. That all space means the point charge, it extends from 0 to infinity. This comes out to be k0 q square by 2 limit r tends to 0 1 by r. This term is indeed very high. So the self energy goes to very high value, and this cannot be, in fact, cannot be calculated. However, strictly speaking, the point charge of 0 radius is not obtained in practice. Even the teeny particles like electrons or protons, they have finite non-zero radius radii. So this expression, this divergence of self energy is nothing to worry about. Rather, we go to the calculation of self energy of a uniformly charged sphere. And so our next topic will be to calculate the self-energy of a uniformly charged sphere. We consider a sphere of radius A, then the total charge Q in this sphere is 4/3 pi r cube, its volume, times rho. Rho is the charge density. Since it is uniform, rho is constant, and we get rho r cube is equal to 3Q by 4 pi. Now just how the sphere of radius r could be constructed. We consider that this layer has been this sphere has been produced by lapping spherical shell one after another. That is to say, at any stage of this fabrication, we have a solid sphere of radius r, and upon this we superimpose another sphere of another spherical shell of radius r plus dr. So we have a solid sphere. It is a solid sphere of radius r. So the key charge within this is 4/3 pi r cube rho. It is the charge within this, and the potential on its surface, will be K0 Q of r by r. So K0 is 4/3 pi. K0 is 1/4 pi epsilon 0. For Q of r, we write 4 pi 3 r cube rho, and when we divide it by r, this is r square. So 4 pi goes, and this simply becomes rho r square by 3 epsilon. This is the potential on the surface of the inner solid sphere. And the spherical shell that we have introduced, the spherical shell has a width r to r plus dr, a shell of radius r to r plus dr. So its volume dv, volume of the shell, is equal to 4 pi r square dr, and the charge within it dq is rho dv is equal to So if we want to bring this shell from infinity to this location, the amount of work that has to be done du is equal to potential times this charge. For potential we write rho r square, this is square, there was a wrong, rho r square by 3 epsilon 0, and for dq I write this 4 pi r square rho dr. So on simplification, this is 4 pi rho square 3 epsilon naught r to the power 4 dr. So the total energy is obtained by integrating this from r is equal to a to infinity. So the total energy u is the integration over du, and this is the constant part 4 pi rho square 3 epsilon naught r to the power 4 dr from a to from 0 to a. the sphere, the shells has been added from 0 radius to radius r, 0 to r. So this is 4 pi rho to the power rho square 3 epsilon naught into r to the power 5 by 5. I write it, it is r to the power 6 by r. Rho, these two can be combined to rho r cube to the power 6. So this is 4 pi upon 3 epsilon 0, and this is 3q by 4 pi whole square multiplied by 1 upon 5r. So this 1 4 pi cancels with this, so this becomes 1 upon 4 pi epsilon naught. Then this 3 cancels with this 3, so this is 3q square by 5r. This is the self energy of a sphere of radius r and containing the total charge q. The same expression for energy can also be obtained from other two expressions available to us. This is so we can also calculate the self energy as this: U is equal to epsilon naught by 2 E square dr. This is over all space. We divide the all space into two parts. One is the sphere of radius r, and the another is the sphere other part. So this is epsilon 0 by 2 E square dv sphere with radius 0 to r. This is spherical shell. Cell with radius r to infinity. So this here the field is the field within a sphere. So we have a sphere of radius r, and for this is the sphere of radius r, so we have to use the expression for the field within this sphere. So if we apply Gauss's theorem, we use a Gaussian surface like this. So the left hand integration for E less than r into 4 pi r square. This is the integral, and times 1 by epsilon 4/3 pi r cube rho. This is the other side. So E will be q upon 4 pi epsilon 0. Q is the total charge. Q will be up 4 pi epsilon 0 r, and there will be a factor r by r cube. This is the field, and for external point field will be r greater than r, will be q upon 4 pi epsilon 0 r square. So if you use the expression, this is the field for region A, this is the field for region A, and this is the field for region B. If we use this, we again come to the expression for internal self energy is 1 by 4 pi epsilon naught 3q square by 5r. Yet another way of calculating this is to use another expression for internal energy or interaction energy is this: U is equal to rho of r phi of r dv where integrated over b. This time integration is performed over a sphere of radius r. So the phi for internal point r less than equal to, this is q upon 4 pi epsilon 0 r 3 by 2 minus r square by 2 capital R square. This is the expression for the potential at an internal point, and rho is the constant. If we use, again we will come to this expression. One thing is that people usually applies this expression of energy for an electron and equate this energy to the rest mass energy of electron. This is the rest mass energy of electron, which gives an expression for r, which is known as the classical electron radius, and it is found to be of the order of 10 to the power minus 17 meter. But this does not match with the experimentally observed extent of electron cloud. This is one thing, that the electron cloud is dense in its central region and it fades away with increasing radius. So electron cloud is not at all an uniformly charged body. Secondly, such classical treatment is not valid at quantum domain. So it is nothing astonishing that this classical prediction fails in quantum domain. Another thing is that this expression can be used for the energy of nuclear fission, and if we use this as the energy for one nucleon, the one proton, then we can multiply it with the number of protons of the nucleus and get an expression for the energy of nuclear fission. For uranium nucleus, the energy is approximated to 1000 MeV. Actually, for uranium 92, it approximately 990 MeV, which matches to the experimental result.